reach what's called critical result shear stress, tau CRSS, critical result shear stress. And the slip would occur when the actual stress of the material is going to exceed that critical result shear stress. It's typically like of the order of several or tens of megapascals. And for the single crystals, there could be multiple slip systems and a variety of different orientations. So the first one that is going to move is the one that's going to fit this condition where the maximum value of the shear stress is going to exceed the average normal stress times cosine lambda cosine phi. And plastic deformation at yield is the onset of plasticity, can be also calculated from this as the critical result shear stress divided by cosine lambda cosine phi, where both the product is maximized here. So once we meet this condition, this is a condition for yield. And what happens is that if we take a single crystal, then they're called slip lines or persistent slip bands that actually comprised of thousands and thousands, maybe hundreds of thousands of dislocations that emerge on the surface. And we can physically see that. Okay, let's do an example problem. There's a single crystal that has the critical result shear stress of 20.7 megapascals and is exposed to the tensile stress of 45 megapascals. Will it yield when phi is equal to 60 degrees and lambda is equal to 35 degrees? And if it's not, what stress level would be required for the plastic deformation to happen? So first we need to calculate the critical value of the shear stress, which is equal to the sigma times cosine lambda cosine phi, 45 megapascals times cosine 35 times cosine 60, or 18.4 megapascals. How does that compare to the critical result shear stress value? 18 versus 20. It's less. So that means that under these conditions, this material is not going to deform plastic. It's not going to yield. And the second part of the problem was asking to find the stress level that would be necessary to cause yield. And we have the equation for the yield stress as tau critical result shear stress over cosine lambda cosine phi. So we have 20.7 MPa divided by cosine 35 over cosine of 60 of 50.5 megapascals. This would be the macroscopic stress externally applied that would cause this material to yield. I want to make an announcement that the next two exams are going to be on paper. Are you happy about that? Okay. I figured it's worth, you want partial credit, you're going to get partial credit. And the other thing I'm going to do is I'm going to give a bonus problem. So if you solve that problem, you can get more points out of 100 than 100. And what it does, it just brings your average up. So if somebody the average on the first test was 70, but somebody got less, and so you can still make it. And my objective is to teach you and not to fail you. Yes? No. Well, the question is going to be from other class. I don't know. I haven't made up the test yet. I can tell you it's going to be on paper. It's not going to be more complicated than what you do in Bible class. It's going to be similar to your homework. I don't think it's going to be fair if you're doing certain types of problems on the help session and for your homework, and then you come to exam and you see something different. Okay? What is your overall feeling about this class? I mean, is it, you feel okay? Is it too much, too little, just enough? Okay? These are slip bands. And this is the orientation of the externally applied stress. And you can see that each grain has its own orientation. You see that? And each one of those grains has its own combination of these two angles, phi and lambda. And the most favorable slip system is the one that's going to be activated first. It's kind of like the weakest link. So, the other thing that we can do through processing is we can cause texture or deformation texture. Here is the microstructure of the material before it was rolled. This is after it was rolled. If you compare these two images, what difference do you see? What is the difference between this one and that and this one, before and after deformation? Compact? Stretched out. Okay, so because it's rolled in this direction, there's plastic flow. And this plastic flow physically causes the grains to elongate. And you can see that they become longer in the horizontal direction than they are in the vertical direction. And as a result, the material becomes anisotropic, meaning that the properties are not the same along the rolling direction and perpendicular to the rolling direction. If there's time, I'll show you a paper that demonstrates that very clearly. Now, how can we make materials, specifically metals, stronger? Through processing. Well, if we increase the dislocation mobility, then it would be easier for the material to deform. If we decrease the dislocation mobility, it's going to be harder. And our process is all about that, making things either softer or harder. So if we reduce the dislocation mobility, it's going to take a higher force to cause the dislocations to move. There are three mechanisms to do that. First one is the grain size reduction. If we reduce the physical grain size, then the dislocation will travel towards the grain boundary, and then it would have to make a turn. This is why if you go on 40th Street, all those roundabouts, you cannot go fast because there's a roundabout. They don't even have to put a stop sign there anymore. Right? The stop sign is much slower because there's no traffic. You can go on the roundabout. You know what I'm talking about? So whenever you have to turn, driving your car, you have to slow down because if not, in case of a dislocation, this dislocation cannot go from one grain directly to the other because that other grain has a different orientation. So it has to take a turn. And when it takes a turn, it slows down. The other one is solid solution strengthening. Solid solution strengthening is when you put other stuff in there. Could be other cars, could be a bunch of stop signs, but secondary particles slow down the dislocation motion. And the third one is string hardening. And string hardening is just generating more dislocation. And that's kind of like what you see if you go and you hit traffic. You cannot make it here. Try to get out of USF at 5 p.m. You have to have extra time. You know what I'm talking about. Or try to get here by 8 a.m. It's not so easy because of the rush hour. Okay, how does this work? As I just explained, we have this extra half a plane, which is a dislocation, and it is approaching the grain boundary. It has to cross the grain boundary and then go into the other grain. This process slows down plastic deformation. So we have here a discontinuity of the slip planes. And you can imagine that this, when you drive your car, you drive on a specific plane. This is in 3 dimensions. And then if we reduce this grain size, it has the effect of more barriers to the dislocation's motion, there's actually a hole patch relationship that relates the yield strength to the grain size D, and here's the equation. The yield strength is equal to sigma 0 plus K times D to the minus 1/2. So this is 1 over the square root of D. And both sigma 0 and Ky are material constants. Now there's been a lot of research in the nanotechnology realm trying to utilize this mechanism. I can tell you personally that it breaks down at the nanoscale, but for macroscopic, for regular metallurgy, it works. And typically, what people do is they plot 1 over square root of D on the horizontal axis, and then this becomes a linear equation. The second one is solid solution strengthening. And the solid solution strengthening, this illustrates how tensile or compressive stresses and strains exist around the dislocation. So here you have an extra half a plane. As a result, there's compression. And you can imagine if you have people sitting right next to you, you cannot lean towards them, especially in an airplane, in a narrow seat. But if there's an empty seat, you can put your person there, you can just kind of lean on the other side. In extra half a plane where there's a dislocation, it's compression. On the bottom, it is tension. So there's a localized strain field around the dislocation. And what we can do is we can actually replace one of the atoms with a different type of atom. And that atom is going to have different properties, different dimensions, different size. Okay? So accommodation for the dislocation could be in terms of the small atoms, like here. So there's an interaction at the atomic scale between those extra half planes of dislocations and the atoms that are placed in the structure somehow. This is an example of the substitutional impurity that is larger. So here you can see that it causes relaxation. Here we have the 3 smaller atoms that are accommodating this dislocation line. Here we give you an example where the atom is bigger physically. So macroscopically, you're not going to see it or you're not going to feel it, but the atomistic scale, this is exactly what is happening. There is the software that you can play with. Again, this is a free visualizing tool. If you ever need to make any presentations, it comes free to everybody, not just if you go online, you can access the virtual material science. What is the motto of this class again? Or the whole holy grail of material science? To control the process, to control the structure, to control the properties. So here's an example of copper-nickel alloy. And this is the plot that shows tensile strength as a function of the concentration of nickel in weight percent. This is the tensile strength of pure copper. And this is the yield strength of pure copper here. So you can see by adding 50 weight percent nickel, we can basically double the yield strength, like tensile strength. And this is the yield strength. You can see here that the yield strength is proportional to the square root of the concentration. Third mechanism is strain hardening. Remember that paper clip? If you start bending this paper clip back and forth, you would realize that during the second, the third, and the fourth time when you bend it, it becomes harder to do that. It's called strain hardening or cold working. Cold working is a process which is shown here in terms of rolling. So there are two rollers that take the material that has the cross-sectional area of A, and after it goes through the rolls, it has the height or the cross-section A sub D. What we can do is we can calculate the percent of cold working as the original area minus the deformed divided by the original area times 100%. If you have a car, the body of the car is made from sheet metal, and sheet metal is made by rolling. So the pressure during processing is so high that metal physically flows like a silly putty between your hands. Or what's the other one that kids play with? Dough? Play-Doh. Yeah. Have you ever tried to put Play-Doh in a fridge and take it out? It's hard. Okay. How many of you use a pencil writing your nose? Okay. Why do you use a pencil? You can erase it. This is the biggest advantage. So we'll talk about this as well. Let's take a look at the strain hardening. Here's a plot that shows stress versus strain for low carbon steel. Okay, so here's stress strain curve number 1 without any cold working. This is 4% cold working, and this is 24% cold working. What difference do you see between these three curves? And you need to keep a note that the material is the same. It's the low carbon steel. This one you can take to almost a quarter in terms of the strain, but it yields at about under 250 megapascals. The one that was cold worked to 4%, we basically almost double the yield strength, but then it fails at 0.2 or 20%, and then the one that was deformed to 24% cold working, we can only take it just past 10%, and the yield strength goes up to 550. Well, we can see that there's an increase in the yield strength from here to here to here. There's an increase also in the tensile strength. Tensile strength is the maximum here. And also the ductility is decreasing. So instead of this, we go back to this, we go back to this. So material becomes harder, and it's harder to deform it. Another thing I want to bring up is if we have extra half planes on top, then if they come together, they start to repel each other. Opposite to the planes that are on the opposite sides. And if you have two half planes coming together, when they come and align, what is going to happen is this dislocation is going to annihilate. Because if you have half a plane on the top and half a plane on the bottom, when they come together, it becomes a perfect plane, right? Okay. So there's attraction force that is acting between dislocations of the opposite sign, but the dislocations of the same sign are being repelled. And we need to introduce a concept and a parameter that is measurable and can be calculated. It's called dislocation density. Dislocation density is equal to the total length of the dislocation lines divided by the volume where they are. And you can see we have the dislocation length. What are the units of length? Meters. And what are the units of volume? Meters cubed. So we have meters divided by meters cubed. As a result, our dimensions are 1 over meter squared. Very often in material science it's expressed in millimeters. So typically 10 to the 5, 10 to the 6 per square millimeter is the density for the undeformed metal. Once it's cold work, dislocation density goes to orders of magnitude, 10 to the 9, 10 to the 10 per square millimeter. This little guy's here, and you can see this is a scale of 0.2 microns, so this is 200 nanometers. These are dislocations, and this is a structure of titanium after it has been cold worked. You can see that as we are increasing the dislocation density, the distance between them is decreasing, so there's going to be more, and that's your picture of a traffic jam at the atomistic scale. And typically these dislocations are repelling each other. So again, try to get out of USF at 5 p.m. You're going to hit traffic, a lot of cars trying to get, and once you're at the red light, how many times you sit there and you have to wait because you don't have enough time to go through this red light. So then you wait for the second one, sometimes for the third one, and that is causing even more traffic. So, it's hard for you to drive when the other cars are around. The same thing for the dislocation. The good thing about it is just like your eraser with a pencil, all of this can be erased by heating it up, by annealing those dislocations out. We can anneal them out. But let's do a problem similar to the one they used to give you an Apple interview, Apple computers. The question is to calculate the yield and tensile strength and ductility of copper that has been cold worked by reducing its diameter from 15.2 millimeters to 12.2 millimeters. And the process we'll discuss, it's called drawing. So there's a tool, and then you pull on the wire, and this wire goes through the orifice, and that's how the diameter is reduced. Okay, so from 15.2 to 12.2. We calculate the percentage of cold working as the original area minus the deformed area divided by the original area. A whole bunch of pi's and 2's cancel out. And we plug in 15.2 millimeters squared minus 12.2 millimeters squared divided by 15.2 millimeters squared, and we get 35.6% cold working. Let's have a look at the data. So this is experimentally obtained data that shows you the yield strength as a percentage of the cold working. This is the tensile strength as a percentage of the cold working, and this is percent elongation as the percentage of cold working, which we just calculated 35.6%. So we go here, and we see that the yield stress is going to be 300 MPa. The tensile stress would be 340 MPa, and we are at 7% elongation. Okay. There is a trade-off between the amount of cold working and ductility, the amount of cold working and tensile strength, and the amount of cold working and the yield strength. So how can you use your eraser? How do you erase your pencil? You go over it with what? Your finger? What's the device? Eraser. Okay. So eraser erases your writing with a pencil. How does it physically work, you know? Have you ever thought about it? It's related to this class. Graphite has layers, and once you're writing with pencil, you leave those layers on the paper. And when you take an eraser, you physically remove those layers, and voila, you have nothing written. So you have an empty blank page, white, right? Here's the tensile strength versus annealing temperature, and we have two graphs here. One is the tensile strength, and the other one is ductility. And during annealing, there are three processes that are happening in the metal. They are recovery, recrystallization, and grain growth. And if you keep it at a high temperature for a long enough time, all the previous processing steps are erased, and the material can become soft again. So in case you cannot do it in one step, which most likely is going to be the case, you would anneal it and then start again. And the idea for the savings of the energy is that you want things to be soft when you're processing it into the shape, but after you're done with processing, you want it hard. Make sense? Okay. Recovery happens to 100 to 200 degrees C. Recrystallization is from 200 to 500, and the grain growth happens over 500 degrees C. And there's a trade-off between ductility and strength. They're opposite. How does recovery happen? It's the reduction in dislocation density by annihilation of dislocation. So we have diffusion, right? We have atoms that are diffusing and they're closing up this patch. The other example is called climb. So here we have the obstacle dislocation, and another dislocation would meet with this dislocation and annihilate it, just like when I said two half-a-planes, they would meet and they would form a full dislocation. I'm sorry, full plane of atoms, not half a plane. And everything here is a thermally activated process, which has what kind of dependence on temperature? Exponential. Remember that exponent? That's where all this stuff is going to go to. Proof here. 33% cold work brass before heat treatment. Look, the same exact sample after 4 seconds at 580 degrees C. To control the process, to control the structure. How did we control the structure here? This is a very different microstructure than here. So we get to see recrystallized grains. And if we continue to 8 seconds at the same temperature, you can see there's kind of like pixie dust magic. You see we have these big grains right here, you can still see them, but within those grains we start to form small ones. They're kind of like blooming like flowers all of a sudden. You see that? 4 seconds. Give it another 4 seconds, and all of those large grains are consumed by the new recrystallized, recovered small grains. It happens between 30 and 60% of the recrystallization temperature in 1 hour. I mean, we have to look at the practical terms. How long are you going to keep it at this temperature? Because you need to have a furnace, right? 580 degrees C. So for specific alloys, the recrystallization temperature depends on previous history, percent of cold working. Imagine you take your pencil and you write on the whole letter paper. Trying to erase that. It's going to take you a little longer, right? The same idea here. It also depends on the purity of the metal, because recrystallization decreases with increasing impurity. And I want to give you another definition. Cold working versus hot working. Hot working is when you are doing your process above the recrystallization temperature. cold working as when you're doing it below the recrystallization point, which is going to be specific for each particular metal, for each specific material. Okay, another stage is grain growth. So first we had this structure. This was 8 seconds at 580 degrees C. This is 15 minutes at 580 degrees C. You can see here that these grains start to coalesce and they become large and they grow. So, this graph here shows a transition from recovery to recrystallization to grain growth. And we can see it in the microstructure, 35% cold work. 4 seconds at 580 degrees C, you start to form small recrystallized grains. At 8 seconds at 580 degrees C, most of the grains are recrystallized, so recrystallization is finished. It happens between 30 and 60% of the melting temperature. So please remember that. And if you know the melting temperature of metal, you can tell many other things of how you're going to process it, what temperature is going to be required to process it. And then finally we have the grain growth. Okay, so we started from this and we ended up with large grains, but you can see that these grains do not have these dislocations. And this process is exactly like writing on a piece of paper with a pencil and then erasing it. This process is called heat treatment. And if you do this repeatedly, you deform your metal, then it goes through heat treatment anneal to become soft again, and you deform it again, and you need to repeat it as many times as needed for you to process it into the shape that you need. So, metals that have small grains are tough and strong at low temperatures. Metals that have large grains have good creep and resistance at relatively high temperatures. So, you need to know what the application is going to be for your product and where and how it is going to be used. There's an empirical relationship that describes how the grains are growing, and if we know the heat treatment time T, we can write that D, the average grain size to the power n, minus D0 to the power n, this is initial average grain size before heat treatment, is equal to K times T, where K is a constant for a specific material and T is the time. And you can see that this grain growth, and the exponent T, the power here is roughly 2. And you can see that the square of the grain size scales linearly with time. So you can make some sort of an assessment. What does empirical mean? Do you understand what empirical means? What does it mean to you? Some graduate student and his professor, back in the day, conducted an experiment where they've taken this sample and they annealed it at different temperatures, and then they measured the grain size using the ASTM. Do you remember the formula? And then they plotted their data. And then they fitted their data using this equation. So there's no like universal law that predicts this. That's what is meant by the empirical. What kind of functions do you know? What's the simplest? Mathematical functions, that's the simplest function. If I were to ask you to make a plot of the price of, I don't know, what's your favorite car? Ford 150 for a year. Can you do that? I'm asking you to plot the price of the Ford 150 since its inception, which was what year? When was the first time Ford 150 came out? You have no clue. I don't know. So you can plot that data. You can plot the price of 150 versus the year. And you're going to see how this curve looks like. Maybe it's a straight line. And if it is a straight line, then it's what? The relationship. It's called, for a straight line, what is it called? A linear relationship, right? And the linear relationship is described in a mathematical function. Y is equal to kx plus b. That's the simplest one. But then, if I ask you to plot the price of Ford 150 adjusted for inflation, that would be maybe a linear plot. Or maybe not. I don't know. Because there was also inflation. When I was a graduate student, you could buy pizza for $4. And the whole pizza. How much is pizza now? 20 bucks? Okay, so for $5 in the 90s, you could buy a whole pizza. Now the pizza is 20 bucks. Same pizza. You see what I mean? Okay. Let's have a look here. This is a very important plot because it's the same plot that shows you the tensile strength for recovery, recrystallization, and grain growth. This is for the annealing time of 1 hour. Initially cold work grains, elongated and textured. During recovery, we're going into the recrystallization, so the new grains half the way start to grow and emerge. And then there's the grain growth. So here, this is the plot that shows the grain size in millimeters. And you can see that it is nonlinear as a function of temperature. Very nonlinear. You understand this part? We cold worked this. It had fine structure, hard. We heat it up for 1 hour at 200 degrees, 300 degrees, 400 degrees, 500, 600, and 700. Kept it there for 1 hour. Can somebody tell me why is this so nonlinear? Or I'll ask the question in a different manner. What is the process of the grain growth? What does it take for those grains to grow? What are they growing? Why are they growing? Yeah? What? Who said something? You're increasing the temperature. And what happens to the atoms when you're increasing the temperature? Yes? They become more active so the material expands. And what does this have to do with the grain growth? Linear expansion? No. Not really. I mean, the reason why there's linear expansion is because if we look back at that potential well concept, the average spacing between the atoms is changing. But they don't physically move. For this to happen, the atoms have to physically move. And what's the mechanism for the atoms to move? Starts with a D. It's called diffusion. And diffusion has exponential temperature dependence. That's why it takes so long, 1 hour, 2 hours, 15 hours, because you need to allow for this diffusion to happen. Apple problem that you're going to ask you when you interview for a job. Cylindrical rod, except that they're going to ask you if you have a sheet of aluminum, how can you process it so that you can bend it 180 degrees? That's literally what they're asking. over and over again, because students reported, oh, I interviewed with Apple, what did you ask you? Oh, 180 degrees aluminum bending. Cylindrical rod that was originally 10 millimeters in diameter was cold work, needs to be cold work by drawing. The circular section must be maintained during deformation. Cold work tensile strength more than 380 MPa and ductility of 15% elongation are desired. That's what you want. And the final diameter must be 7.5 millimeters. So we need to go from 10 millimeters to 7.5 millimeters. Deform the wire from 10, that eventually it becomes 7.5. So let's first calculate the percent reduction of area when we go from 7.5 to 10. It doesn't sound like a lot from 7.5 to 10, but it's actually 44% reduction of area. You see that? So this is brass from 10 to 7.5, 43.8% reduction of area. So we go to this plot of cold working, we go to the 44%, and we see that the strength would be, tensile strength would be 540 megapascals. We also see that the percent elongation at 43% is going to be 6%, and then we compare it to the properties that we desire. It's actually higher than 380. It's less than 15. So we're okay here, but we're not okay here, because the strength is going to be higher than what is required. We will not be able to process it in one step. Does everybody understand why? Because of this requirement that we need to tensile strength of 380 and at least 15% elongation. And we calculated less than 15% and more than 380 megapascals. So what do? The tensile strength is 380. So we plug it into here, and we see that percent cold working for 380 MPa is going to be 12%. We go back to this plot, and we see what would be the requirement for 15%, and we get 27% cold working. So that means that in order for us to achieve this kind of properties, this is our processing window, between 12 and 27%, based on these two criteria. So how are we going to do it? We're going to cold work, we're going to anneal, and we're going to cold work it again. The second deformation step has to be between 12 and 27% reduction of area. So let's make the calculation. The percent reduction of area is 1 minus deformed squared over the initial squared. And we can make the calculation for this intermediate diameter, 7.5 millimeters divided by 20% cold work. That's going to give us 8.4 millimeters. So from 10, we go to 8.4, and that way we can do it in one processing step. Then we're going to heat treat it to allow recrystallization and cold work it again from 8.4 to 7.5, and then we calculate that the percent of reduction of area for cold working number 2 is 20. And the result, we get 20% cold work, tensile strength of 400 megapascals, and 24% elongation. And it requires 2 processing steps for this to happen. Now, very often for, you're going to be taking a course called, it depends what your major is, but if you're mechanical, you're going to take a course in manufacturing processes. And if you're an industrial engineer, you probably are going to take that course as well. And if you're civil, I don't know. The reason if you're industrial, you're going to take that course is because you're going to be there with a stopwatch measuring the time of how long does it take for each particular processing operation, trying to optimize your process. Because your job as an industrial engineer is to find bottlenecks. And if you can have a machine that can have the drawing in one step that would reduce it from 10 to 8.4, and this wire is continuous, so there's a introduction through, it can go through the annealing step and go to the other machine. That's why most of those processing operations are just stacked in line. So you can combine drawing, annealing, and the second drawing into one manufacturing process. But it would require technically 3 processing steps. Cold working from 10 to 8.4, annealing in line, and then second cold working to a 7.5 millimeters. One thing you have to realize is that once the wire becomes longer, then there's going to be a cylinder on which this wire is going to be wound. That's how you buy it in the store, right? So you have one wheel here with your wire that's spinning at a certain velocity. Then it goes through the process, and this wire becomes much longer, so you have to spin it faster. And there are people that do the design for equipment like this. Okay, we talked about dislocations, we talked about atomic distortions and polycrystalline materials, grain size, solid solution strengthening and strength hardening, and heat treatment, which comprises of 3 different steps of recovery, recrystallization, and grain growth. And an analogy is you erasing your writing with a pencil. And you as a process engineer make materials either softer or stronger by deforming them, cold working them, by then annealing them to achieve the goal that you're trying to achieve. Okay? How do you make metals stronger? We just covered the material. I want you to give me some ideas of how you can make metals stronger. Heat treating it. Okay. Deforming it. And what is the mechanism? Why the material becomes stronger as you reduce the grain size? They become harder. Because this dislocation, remember, plastic deformation in materials only happens by shear and the motion of worms, no, motion of dislocations. All right. Have you been to the Tampa port? Anybody? Have you taken a cruise out of Tampa? Not yet? Maybe with your parents? No? Yes? Have you seen the Liberty ship in the port of Tampa? What is a Liberty ship? Second World War, U.S. aid to Europe, there was a need to transport a lot of stuff. How? Through the ocean. And how was it done? By the ships. Why they were called Liberty ships? Because maybe if not for the United States, we'll be speaking German. I don't know. Maybe. I don't speak German, but who knows? How could those ships be made fast? They used rivets before. And then they switched to a different process called welding. They welded the metal. And the problem with the metal that's welded is that there's a continuous path for a crack. And what humans didn't know, what the humanity didn't know about something that's called a ductile to brittle transition. Here's another example. This was not that far ago. Luckily, nobody died. You see this? Fuselage of the plane came off during the flight. So let's talk about failure. The first mode of failure is fracture. And fracture is when something was one piece and all of a sudden became multiple pieces. A quarter. So you can imagine. I can take this quarter, I can try to bend it. It will probably bend. Then I take two pliers and I start to bend it back and forth. And after a certain amount of time, what am I going to have? Two pieces of this quarter. Right? Okay. Now, imagine that this was made from glass. Would I be able to bend it? Okay. All right. What are the three classes of materials? Metals, polymers, and ceramics. And all three are represented in a beverage container. So here's a plastic bottle. Anybody has a metal? Right there's a metal. The drink. Anybody has a glass? Okay.
Does glasses count?
Are your glasses actually? You have real glass, or is that plastic in your lenses? Or you don't know? Are they heavy?
No.
It's plastic. So all those lenses in the newer ones, maybe yours is glass. I don't know. Okay, we do a test. And you've done this test inadvertently in your house. You take a beverage container and you drop it on the floor. Okay? So we drop the plastic bottle. What happens? Bounces down. We take a closed aluminum can and we drop it. What happens? Bounces and there's a dent. And then we take a glass bottle and drop it. Okay. What kind of fracture or glass shattering? What happened to the material, either plastic or metal, when we dropped it? It didn't keep its shape because the one that we dropped in the metal has a dent. So it underwent plastic deformation. The plastic bottle maybe underwent plastic deformation. The glass didn't undergo any plastic deformation. So that behavior is called brittle. The metal plastically deforming is called ductile. So in ductile materials, we have slow crack propagation that is accompanied by plastic deformation. And that gives you some sort of a warning Whereas brittle fracture that's associated with rapid crack propagation, no plasticity, it doesn't give you any warning, it just fails. So what do you want to have in your real life? You want to have ductile failure versus brittle failure. What determines the failure mode? Is the nature of the material and the nature of the atomic bonding. Here's an example of brittle fracture that is subjected to tension. There's no reduction of area. It breaks on the plane of the normal stress. Here is moderately ductile because we started to form a neck due to shear, and this is a very ductile. This is fundamentally very different behavior in terms of the failure from very ductile to moderately ductile to brittle. And here's an example. Both are metals. So it does not necessarily mean that you have a metal that is going to be very ductile. You can see here, there is no reduction of area. The original cross-section remained the way it is. Here's some defect. And this one that shows you cup and cold fracture is moderately ductile. But both are metals. How many of you ever drilled anything? What did you drill? Okay. Have you ever had a bit fail?
Yes.
How did it fail? Okay. It would snap flat. And that bit was, what kind of behavior did it demonstrate? Ductile or brittle? Very good. Have you ever had the bit bend? It happened to me, especially if you buy the bits for wood. If you press too hard, sometimes it bends. It's also catastrophic failure, but it doesn't snap. So what happened to that piece of bit? It flew somewhere, right? Did it hurt somebody? You're lucky. That's why you're supposed to always wear protective gear, protective glasses for your eyes. Your ability to see determines your quality of life. Because God forbid, you can't see, your quality of life just, so please. And this is the problem with brittle fracture. A whole bunch of pieces fly. And here's an example of ductile pipe. Here, you can see that the pipe failed, but it still remains as a single piece. This pipe failed into many pieces. And guess what? This piece is under pressure, flew somewhere, and they become projectiles when this happens. Let's have a look here for moderately ductile materials. First, we apply the normal stress sigma. As a result, we see some necking. Inside the materials, there are some voids that are forming. These voids are coalescing, and then eventually it gives you this cup and cone behavior. Next semester, I'm scheduled to teach fracture mechanics, Tech Electric. This whole class deals with cracks and ductile versus brittle behavior of metals. You can be a detective by looking at the fracture surface and do fracture analysis. This is where the crack initiated. And if I give you a piece of metal, very likely you're not going to be able to break it with your hands. In fact, that soda can, that energy drink can, don't try it at home. But if you wear gloves and you're trying to rip that can, you could by twisting it. I don't know if you've ever done anything like this, or by maybe bending it. You're not strong enough with your bare hands to just tear that metal that's very thin. Yet, at the same time, you can pop the soda can. How do you do that? And why does it happen? The metal on the top is very thick. Have you ever thought about that? Why is it called pop? Yeah. A soda pop. What if the drink is not carbonated? Is it still popping? Okay, look at the design. Look at the design. There's a little lever, right? So you look at your design. Can you tell me why you can open it? A metal thinner. Have you ever seen an antique or antiquated soda can where you actually rip the piece of metal and then that piece becomes a separate piece? You know what I'm talking about? There was a big deal about that because, you know, recycling wise and all that, you would throw away that piece that you ripped. But the reason you were able to rip it is because there's a groove there. There's a stress concentration. Okay. Fracture initiation site allows us to do forensic analysis why things fail. This is a chevron marks over here. And stress concentration is what's causing initially growth of a crack that eventually goes to grow to a large distance, and then the whole part fails. At the material science perspective, there are two types of cracks. The cracks can go along the grain boundaries, you see here, or the cracks can go through the grain. The one is called intergranular fracture, and the other one is called intragranular fracture. They sound very similar, so maybe it is hard to remember. But or transgranular is another word. Intergranular fracture or intragranular fracture or transgranular fracture. However is easiest for you to remember. The bottom line is that for the intergranular fracture, the crack grows between the grains, between, like internship, and trans or intra is through the grain. And the nature of the material determines how the crack is going to propagate. So fracture happens by the propagation of cracks. It's measured through the fracture strength of most materials, and that happens below the predicted theory. Why? Reason number one is because there are flaws in the materials. They're not perfect. And because of the stress that's applied externally that gets magnified inside. Here's a cartoon. Before we go into this, I want to demonstrate. It's a piece of paper. Okay. I can try to rip it with my hands, but it's resisting. You see that? I mean, I could probably rip it. I hope I'm not going to get hurt. And you can do the same thing. So it's hard. Now imagine that all of a sudden there's a little tear. And you see, once there's a little tear, it did not take that much effort for me to tear it, right? I can continue this experiment more, and you can try it. I mean, I'm not putting up a show here. It's hard for me to rip it. I can't. But again, if there's a little tear, look, did not require that much effort. And you can do the same thing. Now let me explain to you why. This is my initial flaw on the surface. This flaw can be also inside. If the flaw is on the surface, we call it A. If the flaw is inside, it's double, 2A. The maximum stress at the flaw is equal to the macroscopically applied stress. I'm applying stress to it somewhere here. It's average stress. It's this load divided by this area. Times the square root of the crack length divided by the crack tip radius. Okay? So look at this mathematically. I just tore a defect. What do you say, maybe 4 millimeters? How sharp do you think is that tear? What is the radius of that tear? It's sub-millimeter. Has to be. So we have millimeters divided by microns. And this ratio is a huge number. See that? So when I macroscopically apply stress to this structure, it averages out. But once I apply the same stress, it gets magnified and it goes right into the crack tip, and it can be magnified by a factor of 100, 1,000, because the crack is sharp and it is long. This is the concept of fracture. Flaws and defects are detrimental, and that's what's causing the failure. And initially, there may be no crack, but there could be a defect, atomic defect, lack of an atom, or a dislocation, or some sort of discontinuity at the atomistic scale. Over time, ultimately causing failure. Okay, I'll see you next week.